Okay, this next lecture is on single slit diffraction. It's section 10.2 in your textbook. So we talked about the double slit experiment, and part of that was to use a single slit and then a double slit in order to get our light to be coherent. But there is when we pass light through a single slit, we do have some diffraction as well. Now let's look first at with a water wave. If we have water that passes through a single slit, what happens is the water starts to radiate out around that slit. So we have that kind of curved pattern. Light behaves the same way. If you shine a beam of light through a progressively narrower opening, the wave properties of light begin to become apparent. So what we need to do is make a very narrow opening in order for us to see it with light. So it says to understand how a narrow opening can affect light passing through it, consider the behavior of light passing through a single slit as shown. So assume the following conditions exist. The width of the slit is narrow enough that a substantial amount of diffraction can occur. The light source is monochromatic, and the light source is far from the slit. So what we end up seeing is a Fraunhofer diffraction pattern. And what that pattern looks like is it's similar to a double slit, but there is a central maximum that is twice the size of every other maximum, every other bright fringe. So the bright fringe in the middle is larger, more intense. And then there's dark fringes, and then there's bright fringes. So copy this down. Single slit diffraction produces Fraunhofer diffraction. The interference pattern shows a bright central fringe flanked by dark fringes. And those minima, those dark fringes, are flanked by less intense bright fringes, which we call secondary maxima. And remember, the central fringe in this is twice as wide. So this changes our calculations a little bit in terms of what it looks like when we're using Fraunhofer diffraction versus the regular diffraction we see from a double slit. And it's sort of shown here in that image in the green. We have our light approaching the single slit. The light radiates out, experiencing diffraction through the slit. In the center, we have the brightest point. And then we have progressively, or I guess you could say regressively bright fringes appearing. So they get weaker and weaker in terms of how bright they are. Now, in terms of the width of these fringes, the width of the central maximum is twice the size of the width of every other fringe. And every other fringe is actually of the same size. So why do these fringes occur, and how can you predict whether bright fringes or where the bright fringes and dark fringes will appear? So the key to answering these questions is Hugin's principle. So remember that Hugin's principle states that each point of a wavefront acts as a new source of waves. So if we're looking at this with Hugin's principle in mind, you can imagine many point sources across the single slit. So at that single slit, we have the sources. Let's just limit it down to 5. 1, 2, 3, 4, 5. So the wavelets produced by each source will interfere with each other, generating an interference pattern on the screen. Wavelets passing through the slit are in phase with each other and interfere constructively, producing a bright central fringe. So 1, 2, 3, 4, and 5 are all constructively interfering with each other. That means the fringe in the middle will be the brightest. However, the wavelets leaving the slit at an angle, so those are the waves that are head-on at a 0-degree angle. The other waves that are diffracting end up being at an angle. They will produce destructive interference for every half wavelength distance, and constructive interference for every full wavelength distance. That's what it kind of says on this slide. Then it says the second dark fringe occurs when the path difference between the wavelets 1 and 2 is exactly 1/2 lambda. Similarly, wavelet 2 and 3 will also strike the screen at exactly 1/2 lambda apart. And then we do this all the way through. Analyzing this geometrically, we come up with this relationship. Sine of theta n, where n is the order number of the dark fringe, is equal to n lambda over w. So this is similar to the destructive interference of the double slit, with the exception that we're not at n minus 1/2, we're at the value of n. And then for the bright fringes, it's the opposite. So we have these bright fringes that will be at sine theta m, where it's m plus 1/2 lambda over w. So again, a double slit experiment for calculating the angle to the fringes. For a bright fringe, we use m as, I guess, a whole number value. For a single slit, we use the m as at the half values. So please copy this down. Remember, m and n are the maximum numbers, and the central maximum is the 0th maximum. So if you we don't actually use the equation for that one. So we start. Actually, I'm not sure if that's. Yeah, no, that's right. Yeah, so we don't start with the 0. Obviously, we start with 1 for our bright fringes. And we start with 1 for our dark fringes as well. So here's a question that says, at what angle will 750 nanometer light produce a second minimum if the single slit width is 2 micrometers? So let's look at this here. I'll pull the calculator up as well. We're looking at producing so the angle. Now but first we have to figure out if we're using our constructive or destructive equation. So it's saying it'll produce a second minimum. The minimums occur with destructive interference. So I'm going to write sine theta n equals n lambda over w. And my theta, I guess you can write it like this, n lambda over w. So my theta n is going to be the inverse sine, and it's which order was this again? The second minimum, so this is going to be a 2. The light is 750 nanometers. And my width is 2 times 10 to the negative 6 because it is in micrometers. So let's solve this. It is 2 times 750 divided by 2, so times 10 to the power of negative 9 divided by 10 to the power of negative 6. So I have 0.75, and the inverse sine of 0.75 is going to be 49 degrees. And typically you're going to write your degrees with, so it's a little bit different in terms of significant digits here, but you're writing your degrees always with 2 significant digits. So if you have an angle that is less than 10, it'll be a decimal there. So it might be 9.8, 8.6. Okay, let's go back to our questions here. This one says, if the first nodal line in a single slit diffraction pattern occurs at an angle of 15 degrees for light with a wavelength of 580 nanometers, what is the width of the slit? Okay, so the first nodal line, so we're looking at a situation where n equals 1, and we're looking at a nodal line. So remember, nodal lines implies destructive interference. because it's the antinodes where we have the bright fringes. So sine of theta n is equal to n lambda over w. We're trying to find the w, so in this case it's w equals n lambda over sine theta n. My n is the first nodal line, so I'm going to put a 1 in there. My light, let me go back here and see, is 580 nanometers. And sine of 15 degrees. So I'm going to do this here. It's 580 times 10 to the power of negative 9 divided by 15 sine. So I end up with, I'm going to round for two significant digits. My W equals 2.2 times 10 to the power of negative 6 meters. Okay, so moving on, let's look at other ways we can analyze this. It says by determining the angle and distance from the screen, the distances between the fringes can then be calculated. So we're looking at finding out what's the it's not the delta x, but we're looking at the distance between. So it would be our yn value, I guess we can say. So that little y distance here, y to 1, y to 2. So from the central maximum, the center of the central maximum to our first dark fringe and our second dark fringe would be y1, y2, y3, and so on. And again, because the distance, because L is so much larger than W, we treat this as parallel. And we end up with this relationship, very similar to what we have for the double slit, although it's a little bit inverted. So you can copy this down. So the distance to the mth maximum is ym, and the distance to the nth minimum is yn. And this is from the center of the central maximum. So let's try a question out. It says light of wavelength 540 nanometers is incident on a slit of width 11 micrometers, produces a diffraction pattern on the screen that's located 80 centimeters behind the slit, so that's our L. Calculate the distance of the first dark fringe from the central maximum. So we're looking at the first dark fringe. So our equation here is yn, because we're looking at dark fringes, NL lambda over W. So we're looking at y1. So the n is 1. The L was, I think, did it say 90 or 80 centimeters? It's 80 centimeters with 3 significant digits, but so 0.800. Lambda is 540 nanometers. And this is all over my W, my width, which is 11 micrometers. So my y1 equals. Now, typically when I do these calculations, I don't reduce the values here just to show you how everything kind of works out. But what I could, using some exponent laws, I know that 10 to the negative 9 divided by 10 to the negative 6 is 10 to the negative 3, so I can just simplify it like that. And then I divide by 11. I end up with a yn of 0.039 meters because I'm limited to 2 because of the 11 micrometers and the 540 nanometers. Those are only 2 significant digits. So in either case, the separation between any two adjacent fringes, the delta y is L lambda over W. Now we have our maximum, which is 2 delta y large. So that's something to consider for this. And we notice that here. Remember, the central maximum is always 2 delta y. So you can copy this down, as well as the note that the central maximum is 2 delta y. And we'll get into some questions here. It says, suppose monochromatic light incident on a single slit produces a diffraction pattern. How would the pattern differ if you doubled the wavelength of the light? So if we double the wavelength of the light, just looking at the equation, if you add a 2 in front of the wavelength, the spacing would double as well. How would it differ if you doubled both the wavelength and the slit width? And if you add a 2 to the wavelength and then add a 2 to the W, the width, the 2 divided by the 2 wouldn't change the spacing at all. So here's a question. It says helium neon light passes through a single slit with a width of 43 micrometers. The screen is 3 meters away. What is the separation of adjacent minima other than the central maximum? So we're looking at the basically asking what's the delta y. So let's look at how we solve this. So we use the equation lambda equals W delta y over L, and delta y equals lambda L over W. So this is delta y equals lambda, which is 6.328 times 10 to the negative 7. L is 3 meters. W is 43 micrometers. So again, I'm going to make this a bit faster by just dividing by 10. So 6.328 divided by 10 times 3 divided by 43 gets me to 0.44. Sorry, 0.044 meters. Here it says light with a wavelength of 670 nanometers passes through a slit with a width of 12 micrometers. Viewed on a screen 30 centimeters away, how wide is the central maximum in degrees? So this here is, we're basically trying to figure out what's the degree to the tip of the central maximum and the degree to the other tip of the central maximum. So this is a little bit of a different question. So in order to find this, we need to find out what the degree to the first minimum is. Okay, so to find this central maximum and its length in degrees, we need to find sine theta n, where n is 1, which is going to be n lambda over w. And that means that theta n is the inverse sine of 1. Our light, can't remember what that was, but this is 12 times 10 to the negative 6. It was 670 nanometers. Notice how I didn't need to use the value that was given in terms of the length for this. So I will put 670 divided by 12 divided by 1,000. I will find the inverse sine of this. It's 3.2. So theta 1 is 3.2 degrees. Sorry, not percent. 3.2 degrees. So what this basically means is we have our central maximum, which is 2 delta y, and then I will have my next values here, delta y and delta y. It is this angle here is my theta 1. And I'll have another theta 1 on the other side. This is also theta 1. So my angle for my central maximum is going to be 2 times theta 1. So 2 times 3.2 degrees. It'll be 6.4 degrees. Now the second part of this question is going to ask, what is the central maximum in centimeters? So to find out what it is in centimeters, I need to find out my delta y. And to find my delta y, I will need to use that L. So I use this equation. The wavelength is equal to W delta y over L. It's similar to that, but we'll just treat it as if it's equal. Delta y equals lambda L over W. So that's 670 times 10 to the negative 9. My W is 12 times 10 to the negative 3. And my L, which I didn't use previously, was 30 centimeters, so I'll put in 0.3. So this becomes 670 times 0.3 divided by 12 divided by 1,000. So my central maximum, or sorry, my delta y is 0.01675. 2 times delta y, let's multiply that by 2, is 0.0335. So my solution here will be 3.4 centimeters. Okay, now turn that off and this off, and we'll move on to so intensity. Now the following diagram shows the intensity curve for single slit diffraction. So as we were saying, the intensity of each of these bright fringes, it decreases as we go along, and we have this this waveform here that kind of is very intense in the middle, and these next few humps are less intense. So one thing that this brings us into is resolution. So the resolution of an optical instrument is its ability to separate closely spaced objects into distinctly different images. So for example, when light from two objects passes simultaneously through a large opening, the light from both sources is diffracted. It produces overlapping diffraction patterns, and the image appears fuzzy but distinguishable. So when we have our light kind of appearing through an opening, we'll have images that appear in kind of two locations. So this gives us a fuzzy look to our images, so they're not resolved into one location. But when we have a smaller opening, the objects are closer together, and the overlapping patterns end up having the images kind of overlapping on each other, which makes it not only blurry but actually difficult to see, because now we have one blur on top of another blur. So this is considered unresolved, so it's hard to see. This happens with headlights, for example, on a car. So in the distance, it's hard to see two headlights if a car is far in the distance, because the lights appear as if they're one light source. As the car gets closer, we end up seeing that it is actually two headlights that cause that. Most observatories' telescopes use curved mirrors. Astronomers use the telescopes with the largest mirrors to view the most distant objects, not only because they collect more light, but also because the large apertures reduce diffraction effects and offer greater resolution. So last thing I want you to do is copy down the definition of resolution in that image below of a fuzzy but resolved image.